Hello and welcome to another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 7, Lesson 1 on Statistical Questions and Measures. So you did work with this in Math 6, but what we want to do is we want to go back and we want to review in Math 7, especially in this lesson, what kind of questions the branch of statistics in mathematics seeks to answer. Because statistics is very different than most things in math. Most questions that you address in mathematics, there's sort of one answer. There's just one answer, how high was the ball hit, how many cups of lemonade were sold, things like that. But statistics is unique in that it answers questions that maybe don't have a single answer to them. So let's get into that right away by looking at what makes a particular question a statistical question. Here we go. All right, so statistical questions are ones that can only be answered by taking into account the variability that exists in a data set. In other words, if all data that we collected was like literally the same thing, so the same number, the same number, the same number, the same number, well, then there'd be no what's called variation. Variation is simply differences between data that we collect. That's it, right? So when a question involves sort of different numbers, when you can't just give one exact answer, well, then it is a statistical question. And let's look at a common example, not a common example, but a good example of that in exercise number 1. How high someone can jump from a standstill is known as their vertical leap height. Which of the following questions below is a statistical question? Explain your choice. Question 1, what is Zion Williamson's maximum vertical leap? So that's our question 1. And question 2, how high can professional basketball players leap? All right, so I want you to pause the video for a moment and think about which one of these two questions anticipates that there will be variability that exists in whatever the answer is. Pause the video now and think about this. All right, well, hopefully you said question number 2, all right? Now, the reason for that is very simple, right? There are many professional basketball players, right? And they have different vertical leaps. They have different vertical leap heights. So, many different players who have different vertical leaps, right? So, I'm not much of a basketball player, and my vertical leap is very, very small, right? And that may be the same for you, or you might have a very high vertical leap. Maybe you are a basketball player, right? And you might think to yourself, yeah, but the people who really can leap high, those are NBA basketball players. And you might even say to yourself, I wonder how high NBA basketball players can leap. Well, that is a statistical question, right? Because there's some NBA basketball players who can't leap very high at all, right? But maybe they're really tall, so it doesn't matter. And then there's other ones that it's like they've got springs attached to the bottom of their feet. Now, on the other hand, a question like number 1, what is Zion Williamson's maximum vertical leap height? So Zion Williamson, right, a very famous basketball player who currently plays for the New Orleans Pelicans, right? He's got an amazingly high vertical leap. And the way that we phrase this, what is Zion Williams' maximum vertical leap height? There's only one answer to that question. I don't exactly know what it is. I think it's around 42 inches or something. He can leap higher than 3 feet into the air. Now, by the way, if I had been a little bit not careful with this and just said, hey, how high is Zion Williamson's vertical leap height? That would actually also be a statistical question because he doesn't jump the same height every time, right? But his maximum vertical leap height, well, that's just one number. So that's not a statistical question. There's some, record that he holds for himself. That's one number, right? And therefore, this is not a statistical question. This one though, right, if I really wanted to answer this question, I'd have to give you a lot of different information. I might say, well, the minimum vertical leap height for an NBA player is this. The maximum vertical height is that. The range of heights would be this. Maybe the average height that they can jump is the following. The median height is this, that, whatever. And all those numbers are what we call statistical measures, right? They are numbers that actually start to answer, right, a question that involves variability. Let's keep going with this. Very important. Now you might need your calculator for just a little bit of what we do today, not much at all, but there's going to be some calculator work. To answer statistical questions, we use graphical displays of the data set along with statistical measures. And again, statistical measures are these numbers like minimum, maximum, median, mode, mean, range. There's a lot of them, trust me. There are a lot of statistical measures, right? And they all seek to give us some information, just like graphical displays do, to help us answer statistical questions. So let's take a look at exercise number 2, where we continue to look at this vertical leap question. The vertical leap heights of 25 professional basketball players is shown below on the line graph, also known as a dot plot. Answer the following questions. All right, letter A, what were the minimum and maximum leap heights in this data set? Well, again, the beautiful thing about a dot plot is that literally you can come along here and you say, oh, well, there was one player that had a leap of 37 inches. There were 1, 2, 3 players that had a vertical leap of 40 inches. So it's pretty easy to figure out the minimum and maximum leap heights, right, for the data set. And those are great statistical measures. The minimum that something could be and the maximum that something could be. Now we have to be a little bit careful when we read a dot plot just so that we make sure we know what the axis goes by. And notice that each tick mark along this axis actually represents a half an inch. So the minimum leap height, right, is actually 30.5 inches. So I can write that down. A lot of times people will just abbreviate the minimum value by using the word min, right? And the maximum is pretty easy as well. That one at least is a nice whole number, right? That comes in at 46 inches. And I really should be using units here because there are units attached, right? 46 inches. Maybe that's actually Zion Williamson's leap height. These are actual leap heights. They are amazingly high. Now, letter B, what is the range of this data set? Now, range has a very simple formula. We'll go through that in just a moment, but range literally gives us a sense for how wide or how much variation there is in a data set. Because the range, and I would suggest writing down this formula, the range is simply the maximum value minus the minimum value, right? The larger the range is, the more variation there is in the data set. And the smaller the range is, the less variation there is in a data set. So we've got 46 inches minus 30.5 inches. That's going to be 15.5 inches. 15.5 inches is our range, all right? You know, and maybe if we looked at, let's say, the range of a different data set, maybe the vertical leap heights of, I don't know, lacrosse players, maybe there would be a smaller variation, or maybe there'd be a bigger variation. I don't know, right? We'll get into more of that in one of the last lessons of this unit when we compare data sets using statistical measures. Let's take a look at one last statistical measure, letter C. What is the mode of this data set? All right, the mode is very simple. It is, by definition, the data value that occurs the most often. Now, on a dot plot, that tends to be very, very easy to see because we simply look for the number that has the most dots above it. And in that case, that number is 39 inches. Right? So, you know, if you really wanted to answer the question, how high do NBA players leap, you might say, well, the most common, at least based on this data sample, the most common leap is 39 inches, right? And that might inform you, like 39 inches. There's 36 inches in 3 feet. So the most common one is actually above 3 feet, 3 feet of vertical leap. It's amazing. It's like in my wildest dreams. Now, the mode is an example of what we call the measure of the center of a data set. And the measures of centers are sometimes the most important statistical measures we have, because the center of a data set is just a single value, right, that serves to represent a typical value of the data set. There are many different measures of center, many. But the 3 most common measures of center, the only ones that you're responsible for knowing, really all the way through high school, are the mode, which we just talked about, the data value that occurs the most, the median, which is the data value that lies right in the middle of a data set if you put it in order, and the mean, let me just kind of bring this up a little bit so you can actually see it, the mean, which is what we most of the time in the real world call the average, right? And the mean is simply calculated by finding the sum of all the data and then dividing it by how many data values there are. In normal data sets, ones that aren't kind of crazy with crazy distributions, the median and the mean tend to be very close in value. The mode is probably the least used of all measures of center. I mean, it's a very easy idea. Oh, which one occurs the most often? But there's oftentimes data sets that either have no mode or the mode's not a very interesting number because you don't really care how many, or which data point occurs the most often. All right. So the median and the mean are the ones that we're going to use the most often. And again, you would expect, right, if somebody asks the question, well, how high can NBA players leap? What is their, vertical leap? You'd almost expect somebody to say, well, on average, they leap about 40 inches tall, 40 inches high, on average. And when they say something like that, they're talking about the mean. Okay? So let's work with these statistical measures in exercise number 3. The weights of 15 kittens, 15 kittens at a pet shelter are shown below in ounces. When all 15 kittens were weighed together, their total weight was 207 ounces. Letter A, what is the median weight of the kittens? All right, now you are going to find a ton of medians in this unit, all right? And the median, remember, is that number that's right in the middle. It's kind of like when you're driving down a road, the dashed line, that dashed white line that goes down the center, or orange line, or whatever it is, right? That's the median. The median is the thing in the middle. Now, how do you find the median? Well, students do this in a variety of different ways. One way of doing it, and let's keep the camera on me for right now, is by literally just taking their fingers and kind of counting inward like this until they find the number that's right in the middle. All right, that's fine. What I tend to do, especially when there's an odd number of data points, is I do something like this. I take one away, right? So let's say there's 14. And then I take that 14 and I divide by 2 and I get 7. Now, why do I do that? Well, 1, 2, 3, 4, 5, 6, 7. Here's 7 data values. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Here's 7 data values, right? So there's 7 below, 7 above, which means right here, my median, is equal to 13. And we'll talk a little bit what you do to figure out a median if there is an even number of data points. But if there's an odd number of data points, there's going to be one number that's right in the middle. And you can kind of figure out what its position is literally by taking the number of data points, 15 in this case, subtracting 1, dividing that by 2, and then that tells you how many there are below the median and how many there are above the median. You can't see that 7 very well, but it's there. Now in letter B, let's take a look at what we're asked. Is the mean weight of the kittens greater than, less than, or equal to the median weight? Justify. All right, well, let's review the formula for the mean, right? The formula for the mean, right, is to sum the data, literally add up all the data values, and divide by the number of data values. Now, this part of this formula, sum the data, right, you have to be exceptionally careful with. And for real statistics work, when you have 100 data values, 200 data values, 1,000 data values, whatever they are, you never do those sums by hand. You don't even do them on a calculator because, quite frankly, the possibility of entering a number wrong or missing a number, especially when you have numbers that repeat each other, that's really the possibility that that's going to happen is quite large. Most real statistics is done on what are called spreadsheets. One common one is Microsoft's Excel program, all right? Or let's say Google's Sheets program, right? These things would add the data set all up without you having to do anything other than saying, add all the data points up. Now, if we had to add up all these data points, we'd want to do so extremely carefully. But the problem here tells us what their sum is, right? It literally says, when all the kittens were weighed together, their total weight was 207 ounces. That is the sum of the data, right? So the mean in this case, let me get rid of my, bounces all over the place. The mean in this case is going to be that sum, 207 ounces, divided by how many there are. There are 15 kittens, right? This is where we might want that calculator just because, it makes it a little bit easier. 207 ounces divided by 15 kittens, right? And that tells us our mean is 13.8 ounces. And so what we see, right, the question was, is the mean greater than, less than, or equal to the median? Well, the mean is 13.8 ounces. The median is 13 ounces. So let's put our answer over here. The mean is greater. Right? The average is greater. One thing I'd like to point out, and this is constant confusion for a lot of students, notice that the mean is 13.8 ounces, right? That's not one of the data points, and that's okay, right? Very often, the mean, the average, isn't one of the data values. Could it be? Sure, absolutely. But it doesn't have to be, and it often isn't, all right? So the mean and the median are often quite close to each other, right? But don't have to be the same number. And most of the time, quite frankly, they're not. All right, let's take a look at one more situation. The median, or that middle number, can be tricky to find if the data set has an even number of values in it. In this case, we find the average, or the mean, of the two numbers that are closest to the middle. So let's refresh how that's done in exercise number 4. 8 cousins attending a family gathering. Their ages are shown below in ascending order. That means increasing order. So 3, 3, 5, 8, 9, 12, 12, 14. What is the median ages of the cousins? Well, again, so in this case, right, we've got 8 different cousins, right? So obviously it's an even number, right? And obviously 8 divided by 2 is 4. So that means literally this is the lower half and this is the other upper half of the data, so there is no number right in the middle. So what we say simply is this. The two numbers that are closest to the middle are 8 and 9, okay? And we need their mean. If you can do that in your head, if you can just look at 8 and 9 and think, oh, the number that's right in the middle of those two, because that's what you really want. You want the number that's halfway between 8 and 9, which is 8.5. But if for some reason that's not obvious to you, then what you do is you simply take those two numbers, right? You add them together, divide by 2, find their average, and if you did that on the calculator, you'd find then that the median is 8.5. And again, notice the median certainly does not lie in the data set. There is no 8.5 here, but that would be the median age. Now, letter B asks us, what is the mean age of the cousins? All right, this is a relatively small data set. So in this data set, we didn't give you the sum of all their ages. We want you to do that yourself, preferably on a calculator so you don't make any kind of small mistakes here or there. All right, so why don't you pause the video now and figure out what the mean age of the cousins is. All right, well, one thing that we have to do is we simply just have to add up all the data, okay? And again, to do this, we just want to be kind of careful. So we're going to have 3 plus 5 plus 8 plus 9 plus 12. Now I regret not giving you the sum in the first place, plus 12 plus 14. Enter. All right. So the sum of their ages was equal to 66. So the mean will be 66 divided by 8. Let's see what that is. We can just do divided by 8 because it'll take my previous answer and do that. And that is 8.25. All right. So we've got both a median 8.5 and a mean 8.25 that don't lie in the data set. Now you might even say to yourself, but wait, we measure ages in whole number years, so you can't have that or that. Nope, doesn't make any difference, okay? These are simply statistical measures. They don't have to be something that could lie in the data set, and that's important. Because let's say I had 2 kids, and a friend of mine had 3 kids. And I said, what was the average number of kids we have? Well, if you added the 2, the 3 together and you divided by 2, the answer would be 2.5 kids. Can somebody have 2.5 kids? No, of course you can't have 2.5 kids, right? But that's not the point. The point is it's just a statistical measure. It doesn't have to be a realistic data point. Let's look at the last piece of this. Letter C. This data set is considered bimodal. What do you think this term means? Pause the video now, take a look at this data set, and why do you think this data set might be called bimodal? It almost sounds like a singing style or something, bimodal singing. No, I mean, bi means 2, modal has the word mode in it, so literally bimodal means a data set that has 2 modes to it. Well, does it? You bet. Because the number 3 occurs twice, the number 12 occurs twice, right? So there are 2 numbers that occur sort of more than any of the other numbers. So literally this data set is called bimodal because it has 2 modes. And that is extremely common. You could certainly even have a data set that is trimodal, a data set that has 3 modes. Quite frankly, once you get to a point, if you get to a point where like all the data points, none of them show up more than any of the other ones, right? Then we just say that the data set has no mode. And again, in this case, the mode really doesn't make a lot of sense, all right? Here's a situation where the mode might make sense. Let's say you were throwing a birthday party or something like that, and it was for a bunch of 7th graders. All right. So let's say the majority of the kids there, let's say there were like 8 kids there and like 6 of them were 13 years old, right? Maybe you had an older sibling who was 18 years old and then, like a baby sibling that was, I don't know, like 2 years old or something. Then the mode would make a lot of sense. It would make a lot of sense to say, well, there are more, 13-year-olds at this birthday party than any other age. That's an example where the mode makes a lot of sense. When there's this number that like, wow, because that number is really like out there and it's, there's more of them than anyone else, then that should be our measure of center. But the vast majority of times when we're thinking about measures of center, we're talking about the median, we're talking about the mean or the average. All right, let's wrap this up. So today we talked about statistical questions, and it's really important to understand this idea, right? There are certain questions that we answer with all types of math that aren't statistics. And then there are certain questions that we can only answer with statistics because they don't have just a set answer, right? Let's say you wanted to become an app programmer, later on in life. You might be curious, how much money do app programmers make? Well, that's a great statistical question, right? Because there is no set salary for them. So maybe, you'd want to know the minimum salary, the maximum salary, the average salary, the median salary, the modal salary. Maybe the range of salaries. You'd want to know all that kind of stuff. Maybe you'd even like to see some kind of graphical distribution of 100 salaries that app programmers make. All of these things would help you answer the question, how much money do app programmers make? And yet at the same time, there still wouldn't be a single answer. All right. Well, of course, since this is lesson 1, we're going to work a lot more with statistical questions and their measures as we proceed through this unit. For now, I just want to thank you for joining me for another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.